Chapter 12, the Laws of Thermodynamics. The first law of thermodynamics tells you that the internal energy of the system, U, can be changed, can be increased by adding energy to the system. Let's call it heat, plus doing work on the system. This is the usual equation used. I don't know if this is both of these, doing work on the system and adding heat to the system. I think that should be adding heat to the system or doing work on the system. There are many processes through which this could be accomplished. We're going to call them, for example, adiabatic, isothermal, isobaric, and isovolumetric. And this is just a for example. But the basic principles is in adiabatic, there is no heat exchanged. Isothermal, the temperature does not change. In isobaric, the pressure does not change. And in isovolumetric, the volume does not change. All of these are non-chemical reactions, so the number of particles does not change. The chemical energy, there's a couple other details, chemical energy and which changes a lot when you're going from, say, one chemical to another. For instance, when oxygen is used as fuel. And there's latent heat energy when object is changing states from solid to liquid or liquid to gas, or possibly even gas to plasma. So there are many processes through which adding energy to the system and doing work on the system can be accomplished as long as energy is conserved. Second law of thermodynamics constrains the first law. It constrains the first law by establishing which processes allowed by the first law actually occur. For example, the second law tells us that energy never flows by heat spontaneously from a cold object to a hot object. One important application of this law is in the study of heat engines, such as in the internal combustion engine, and the principles that limit their efficiency. Now, when dealing with a gas, one of the main equations is that work is negative P delta V. This is work is in joules, which is kilogram meters squared per second squared. Pressure is in newtons, newtons per meter squared. Delta volume is in meters cubed, so this is in Newton meters. So this might be written as work sub gas, which means work done on the gas. And this is the convention used in this book. Whenever they use the W alone, it's going to be the work done on the gas. Now that's put together with the equation, the change in internal energy in the gas is equal to the heat added to the gas plus the work done on the gas. Also, the ideal gas law applies, so PV equals nRT. We also make these other two assumptions, that every part of the gas is at the same temperature and every part of the gas is at the same pressure. So this kind of puts a constraint on how fast the reaction we're talking about is occurring. Our modeling of combustion, for instance, might be a little bit flawed because we'll be assuming that all of the gas ignites at the same time. First example talks about work in a gas cylinder. You'll notice in this case, when we push this cylinder down or let it come up, our change in volume is non-zero. The pressure will increase as we squeeze that down, so the change in pressure is non-zero. We know because pressure times volume equals nRT that the gas will heat up when you push the cylinder down, so change in temperature is non-zero. This is going to be called an adiabatic thermal process, and the only thing that is kept constant during this process is going to be the heat. The heat exchanged between the gas and the outside world is going to be approximately zero because very little heat is going to escape through this surface. We apply a force slowly to compress the gas. Compression is slow enough for all the system to remain essentially in thermal equilibrium. That means we can use the equation PV equals nRT, because only in the case where everything's in thermal equilibrium does pressure or temperature really represent, properties of the entire gas. These are properties of the entire gas here. If things weren't in thermal equilibrium, then you might have a different property, a different temperature over here than you have up here. You have this thing slamming down really hard. The temperature up here might be considered higher because the average transverse kinetic energy of the molecules up here is going to be greater than that on the ground. And here is the equation I gave you. Here, the work done on the gas is negative P delta V. By the way, the work done on the environment is P delta V. That's just kind of the equal and opposite work done. So that's the amount of work done on the piston, for instance. The delta V here is going to be negative, so when you put a negative delta V in there and a negative sign, this is going to be a positive work done on the gas and a negative work done on the environment as you squeeze the gas. So since delta V is negative, negative P delta V is positive when the gas is compressed. So that is work done on the gas is positive. And when the gas is allowed to expand, the change in volume is positive, and the work done on the gas is negative. And finally, when the volume remains constant, no work is done on the gas. You might still have a change in energy in the gas because of the heat, but if there's no volume change, there's no work done on the gas, so this part is zero. I'll stress this convention again. In this book, W specifies the work done on the gas. WENV is used to denote the work done by the gas. The work done on the gas is negative of the work done by the gas to the environment. Now, a disqualification of what we have done up to this point. Only when the pressure remains constant during the expansion and compression do you have an isobaric equation. And the previous work equation, namely the equation that we've been using, this one that I've been acting like is a general thing, pressure equals negative P delta V, can only be used for an isobaric process. That means, in particular, in this situation that we were talking about, working gas in a cylinder, the delta, what was it? In this particular example, as they're drawing the picture, you cannot use this equation because the pressure inside that gas is going to be growing as you push this cylinder down. So to introduce this topic, we've already started you with an adiabatic example and an isobaric equation. Let's see if we can remedy that in the next video.